kind of everything that we have been doing up to now has led up to this unit, which is, in my opinion, probably the most challenging unit of all of them, because of just the knowledge that you need and thinking that you have to put into place, and obviously your knowledge of calculus, right? Now, what we've been doing in the last unit was when you have a graph that runs, like this, now we can find the instantaneous slope at any time on that graph. And you've never been able to do that before unless you kind of, picked 2 points, there and there, made a line, right, and got an approximation at those 2 points, right, which was limits. And you've always known how to do that with 2 points and slope. But now we have a tool to be able to find it at any point quite easily. Now, an example of what we're going to do today, or this unit, is what if I had a cone and I had it full of water, okay? And if I put a hole in that cone, obviously the water would rush out, right? Now, what's very different from a question like this and a question like this, oops, I should probably make that, is that if you had a hole here, do you see how the height would be very consistent? The decrease would be very, very consistent all the way down. That height would stay consistent, right? But what happens when you have a cone and you were draining it? Do you think, what thing would happen? Would it go down the same all the way? It goes slow, right? And the height will change more and more as we go down. The change in height is much faster because the radius changes, right? Radius doesn't change here. It's very consistent. So with calculus, we have the ability at any point to tell you the rate that height is decreasing. Because the radius changes every time, right? The height of the water will not be consistent. And without calculus, you can't find the rate the height is decreasing at any point in time, because it's changing every single millisecond. The radius changes. Yes? Well, because physics is rates. Kilometers per hour, right? Lots of rates in physics. And when you're talking about driving to Calgary, right, your rates are very, very different. No one puts the cruise control on from their house at 120 kilometers an hour and goes all the way to Calgary, and at their destination they just reef on the brakes, slide in, and they're like, yeah, 120 all the way, right? It's very inconsistent. If you've ever driven, you're passing, you're pulling over, you're obviously increasing and decreasing velocities as you go. So because of calculus, we're able to find out instantaneous rates of non-uniform situations. And let's face it, your drive to Calgary, very non-uniform. Okay, you are not going to just hit 120 at your house and finish at 120 there. Okay, now that's how they teach us physics when we first start. Okay, because they don't want, right? They don't want to confuse us. Let's just keep it simple. Uniform motion, right? You look back to science in grade 7 when you start graphing, right? These will be your graphs. Okay, it'll be something like that. That'll be your graph, right? Find the slope. Find the slope. What does the slope mean? Okay, this is kilometers, this is hours. You're like, hey, slope is speed. Yeah, right? Now, this, like, where does this happen, right? Where do you actually have that? Where, this might be something, right, that you could have, as you right? This might be something we need to be talking about. Okay, and what does that mean? So we're going to address that starting today. Now, there's two things that, and then if you've been in physics, this stuff's all going to make sense. But let's talk about 3.1. We're in velocity, okay? Now, we're going to first learn how to do even one-dimensional graphs, which are not as simple as the name sounds. Two-dimensional make a lot more sense to people, but we're going to start with one-dimensional. But what is position? Now, position, the position S of an object is its location relative to some origin. And we usually call that position 0. Now, position is what we call a vector quantity, which means that it shows both magnitude and direction, which is when students first learn this, becomes very, very hard for them, because they'll see something like -6 and not really understand what that negative means anymore, because it used to mean, well, that was like minus, right? But -6 just means maybe you're going south or you're going east at 6 kilometers an hour, right? And that, for some students, they're like, whoa, okay, what? So now that doesn't even mean like slowing down and speeding up? No, it doesn't, right? It has to do with what direction you're going, right? So our magnitude is how far the object is from the origin. And direction, shown by sign, of the number. So when we have our compass, never eat soggy wieners, right? We're going to always count north and west and east. Oh, sorry, I screwed that up before. North and east are positive, and south and west will be negative. Okay, and then we can also put in left and right. Shown by sign of the number. So we could say -6, right? That the magnitude is 6 and the direction is negative. So the direction would be down, or, yeah, so I should put that, this would be up and down as well. Right? Down is considered negative, up positive, right and east are positive. Okay, so we want to keep those synonyms in our head. Now, we're going to always talk about distance versus displacement. Now, distance is scalar. So this is the length traveled by the object. Okay, distance is always positive. Okay, and this is what you would, I would say, would be on your odometer of your car. Okay, if you drove, say, let's just for ease of use, let's say it's 300 kilometers to Calgary, and I drove to Calgary and back, my odometer would say that I put on 600 kilometers. Okay, that's the distance that I went. Now, what would my displacement be if I went from here to Calgary and back? 0. Okay, because I haven't changed. Right, I started here, right, went there and came right back. So displacement is always delta S. Now remember, this is a vector quantity, and it is the change in position during the start or during the time period. So it is the straight line distance from start to finish. Okay, and again, it's a vector quantity. Okay, now let's just look at this graph here. Okay, this is a one-dimensional graph. So if at 0 seconds, starting right now, I'm at this spot right here. This is where I start. Okay, now after 2 seconds, what is the distance I have gone? 5 meters. Okay. What is my displacement? 5 meters. Okay. Now remember, displacement is S2 minus S1. S2 is 10 meters minus 5 meters equals 5 meters. Now after 4 seconds, what is my distance? 10 meters. What is my displacement? 0 meters. Now what is my S2? So 5 meters minus 5 meters equals 0 meters. Now after 8 seconds, what is my odometer saying? 20 meters. I went 5, 10, 15, 20. What would be my displacement? Negative 10 meters. Now that would be negative 5 meters, right? Minus 5 meters is negative 10 meters. Now, just to give you some bearing on what a two-dimensional graph would look like, because you're really used to two-dimensional graphs. So if this is time and this is distance, we started 10, 15, 20. So we got 5, 10, 15, 20. So this is a 2D. Okay, we started at 0 time. We started at 5. Okay, then after 2 seconds, we were at 10. Then at 4 seconds, we were at 5 meters again. And after 6 seconds, we were at 0. And at 8 seconds, we were at negative 5. So it would look something like this. Well, yeah, but this is where we would be, right? This is this graph. This is a one-dimensional graph. This is a two-dimensional graph, right? And we're not doing any of this right now. I'm just showing you the difference between a 1D and a 2D graph, right? Because the 1D is actually more new for students, right? They're usually used to this. Okay, note when an object changes direction, distance and displacement are no longer equal. Okay, I think we displayed that by that example. Okay, so let's do some more physics. Average velocity, the rate of change in position of an object, its displacement over time, delta S over t. Okay, so this would be, this would be position. This would be time. Okay, now what is the best way to find average velocity? Would be to, you've got 2 points, right? So, right, there's my 2 points. I got point 1, I got point 2. Go find the average velocity. Now, on a position time graph, that represents the slope of the secant line. Now, instantaneous velocity, this is the velocity at 1 instant in time. This represents the slope of the tangent line. So V equals the limit as delta t approaches 0 of delta S over delta t, right? Like if you want instantaneous, your delta t should be 0, right? How much time goes by in an instant? Nothing, basically, right? Like right now, what is it right now? Okay? So velocity is ds over dt, or S prime. Oh, I got a thus. Thus, velocity is the derivative of a position time function. So V equals ds over dt, or S prime t. So just to restate, velocity equals the derivative of position time graph. Okay, so if V is greater than 0, right, which is moving in a positive direction, so forward, upward. Okay, if V is equal to 0, then it is at rest. If V is less than 0, then it is moving in a negative direction. Backward. Downward. Okay, so the thing to do is not forget what the graph is doing. Now here, this is distance, correct? And this is time. So as time is going, what is happening from here to here? I'm going away from the origin. So this could be Edmonton. And I'm going to Calgary, right? And what's going on here? What's happening is my distance away is getting less. I am getting closer back to Edmonton. Yeah, exactly. Yeah. Okay. Except he must have jumped out of the car in Red Deer when you weren't looking, because obviously you did not slow down. That's how much you love that child. Got over here, right? You were nice enough to actually slow down and open the door, and then back to Calgary again, right? Now, what kind of things we can say? Well, first of all, velocity here is greater than 0. Does that have anything to do with how fast I'm going? What has to do with how fast I'm going? The steepness, would it not be? Right? Which is your velocity. Right? So you can even kind of, maybe by just looking at it, maybe went to B, you know, at a pretty good rate. At B, there was a point where it did stop. Okay? Because this V equals 0. Then from B to C, velocity is less than 0. Does that mean velocity is small because it's like -8? Negative small, isn't it? It's the direction. I'm going 8, whatever, kilometers per hour, coming back, right? This would be another V equals 0. And then this would be V is greater than 0. Okay, now this next thing, by using both the position and the velocity, we can determine whether the object is moving towards or away from the origin. Now, in all of this graph, what can you tell me about S? This entire graph. What was displacement? It was positive, correct? So with positive displacement and positive velocity, we know we're getting farther away from the object, or from the origin. With positive displacement, see, or S, right? Positive displacement, but negative velocity, we are getting closer to the origin. Okay? So if S and V have the same sign, it will be moving away from the origin. Okay, that's important to know. If they have the same sign, they will be moving away from the origin. If they have opposite signs, they will be moving towards the origin. Right? So, do you see that if we had let's just like, see at this point here, do you see we have positive S, because this is S, right? This is, I'm going to do this in black. This is my graph in black, or the X and Y, and this is T. So this is a positive S, this is negative S down here, right? If we have positive S and positive V, do you see how we're getting away from the origin? Positive S, negative V. We are getting closer to the origin. Then we get to here. See how we have negative S and negative V? Same sign. Therefore, getting away from the origin. Here we have negative S, positive V. It's opposite signs. We will be getting towards the origin. Okay? So when we're talking about moving away from the origin, they have the same sign. Now where is that happening? Away from the origin. So let's call this A. it's happening there, we're away from the origin, and from there to there, right? B is if they have opposite signs. Well, here's positive S, negative V. So this would be B. This is as we're moving towards the origin. Okay, this would also be B. And then this part, once you cross that would be A again, right? Okay. So a stone is thrown from a cliff at 80 meters, 80 meter cliff, sorry, until the velocity of 15 meters per second. Find the velocity at 1 and 2 seconds if s of t equals 80 minus 15t minus 4.9 t squared. Anyone recognize this? Where does that come from? Yeah? Anyone recognize this? What is A? Due to gravity. What is it? 9.8-ish? Right? Okay. Now, it's pretty cool. Maybe you don't think it's cool. But if you take, like that's the distance formula. If you do the derivative of the distance formula, you get the velocity formula. And if you take the velocity formula and do derivative, you get the acceleration formula. Like, that's just weird.
So it just flips.
Yeah, it's so velocity at time t equals, well, the derivative of 80 is 0, minus 15t is minus 15 minus 9.8t. Okay, so if you do, well, I want to know the velocity. What's the velocity of this thing at 1 second? Negative 15 minus 9.8 times 1. And you get negative 24.8 meters per second. Now, again, if you're a visual person like me, this is what was going on. Okay, you threw this rock, okay, and it's kind of like, it's doing this, right? So I would expect that to have negative velocity, right? Does negative mean it's slow? No, it means it's going down. Okay, so this is down at 24.8 meters per second. Now, velocity at 2 seconds. Okay, now if this is a good example, I would expect my velocity to be getting greater. And again, someone will go, but it's not greater. It's negative 34.6. That's way smaller than 24. No. It is going down at it's going down at 34.6 meters per second. That's all the negative means. Yeah, I think that's when they first started it. That was the initial velocity. Yeah, they threw it. Okay, the distance traveled by a car is given as 160 t squared plus 20t, where t is measured in hours and s in kilometers. Oh, yep. Yeah. Yeah, because if at 1 second, I can put 1 into here to find out how far it has gone in 1 second, right? And then do the derivative, and you can tell me the velocity at that 1 second, and you could tell me acceleration if you did another derivative at that. So you'd think that you'd have to have like a whole other separate set of data, and you'd have to have like the radar gun and everything. And you can not even be out in the field, take that formula and do a derivative on it, and you get it. Like, it's weird, right? And when I took physics, you never saw that this formula actually came from that one, right? Yeah, I just thought another scientist sat by a hill and did a bunch of stuff and came up with a formula. That's what I thought, right? You know, they figured out, I mean, I bet you that's how they found acceleration to gravity. They just kept doing it over and over and over, and they got 9.81 meters per second squared. That's what it's going to be from now on, right? So you don't really think of like math doesn't work in horse racing, right? There's too many variables, right? You know, if that horse is hungrier today, if that one is like, you know, got a bit of an injury, or all these factors, right? You don't think you can actually do a mathematical formula on something and find out something that you just thought was arbitrary. Now, here's another one. We have a distance traveled by a car is s equals 160t squared plus 20t, where t is measured in hours and s in kilometers. When did the velocity reach 100 kilometers per hour? Okay, yeah, let's do ds over dt. So you'll find that we're always going to be doing our derivative to time. So that would be, which equals v, correct? Which equals plus 20. So with just that simple little move, I can now find the velocity at that time. And it all comes from the graph, right? It was a distance time. This is actually the slope. It's instantaneous slope at that point. I could do a limit at that time, do it old school, draw a little line, and I should come up with a very similar answer to what this will get me. Now this one says, what was the time, right? When did the velocity come to 100? So I'm going to go 100 equals 320t plus 20. We want to subtract 20 to both sides. We'll get 80 equals 320t. We'll divide that out. We'll get 1/4 equals t. So that's 1/4 of an hour, which equals 15 minutes. So the car reached 100 kilometers per hour in 15 minutes. Might want to get a tune-up on that car. Yeah, that's true. Actually, I got a speeding ticket one time in a... Everybody gets speeding tickets, and teachers are people too. Okay. And, but I wasn't speeding. I fought the ticket. I won. Yes, I did. Well, you don't get a refund. You don't pay it. Yeah. But it was a biggie. It was like $320. I'm like, I wasn't speeding. Right? And, you know, they were pulling over car after car after car after car, right? I could see it. Right? Slowed down. And you know what? I'd have to go through that all the time anyway. By that, I slowed down. And, yeah, I did some, because what he had, you know, got me at, it's impossible. So, yeah. Know your physics, it pays off. Yes, physics equals money. Yeah, well, if you found out that you were speeding, you just don't fight it, right? Ignorance always costs you money. Always. Okay, anyway. The position of a particle is given by s equals t squared minus 4t plus 4, where s is in meters and t is in seconds. So always keep track of the time. Last one was hours, right? So when you're putting in t, or you're looking for t, make sure you're aware. Find the velocity after 1 second, after 3 seconds, okay? So we're just going to go v equals, what's my derivative? Minus 4. And it's almost like we're doing derivatives that we learned before we even did derivatives, right? How easy these will be. You could see the stuff we were doing on our test. Like, how is that even going to come into a formula, right? So, I mean, we were doing some extremely high level derivatives where almost to the rest of the year, you're not going to see anything even close to the difficulty of those derivatives. So when you learn derivatives for the sake of derivatives, you can get kind of nasty, right? But when you're working with these kind of formulas, the derivatives are going to be extremely simple. So what's the velocity at 1 second? 2 times 1 minus 4. You get -2 meters per second. What's the velocity at 3 seconds? That's 2 times 3 minus 4. 6 minus 4 is 2 meters per second. Okay, now this is a, do you recognize this shape? It's a quadratic, so it will have your horseshoe, right? So that's what's going on, right? And to have a little bit of knowledge of the graph you're doing, well, that kind of makes sense, okay? That there was a time that it had negative velocity, and then there'll be a time where it has a positive velocity. That's pretty accurate with a, and if that was a negative t squared would be your other parabola having a positive velocity, 0, and then a negative velocity. So when would the particle be at rest? Well, right there, right? 0 velocity. So rest at v equals 0. So 0 equals 2t minus 4. T equals 2 seconds. Okay, because you're going to add 4 to both sides and divide by 2. So you're kind of getting an idea, right? That's 1, 2, 3 of your graph. And then you'll start to see when we get into curve sketching, which is next one, how you can start using this to get a visual of the graph. Now, when is the particle moving in a positive direction? Yep. We don't know that for sure, do we? Yes, we do know that for sure. Okay, but let's see when is 4t or 2t minus 4 greater than 0. When 2t is greater than -4, when t is greater positive 4, t would be greater than 2. Okay. Now draw a diagram to illustrate this motion. Now, I drew you a 2-dimensional. What would a 1-dimensional look like? I find the 1-dimensional much harder. I think it's just how we think. It'll be different from person to person. So, we've got time of 0. This is our time, right? 0, 1, 2, 3, 4. So remember we have this formula, S equals t squared minus 4t plus 4. So S at 0 time would be 0 squared minus 4 times 0 plus 4 would equal 4 meters. So I am here starting. Oh, so what am I doing? That's not time. Yeah, so this is, yeah, for 1-dimensional, you don't have, it's always, this is always going to be displacement, right? So you can write on here, t equals 0. So let's try finding the displacement after 1. Okay, so that's 1 minus 4 plus 4 equal 1. So I am over here at t equals 2 seconds. Oh yeah. Okay. Told you these are confusing for me. S of 2. That's 4 minus 8 plus 4, which would be 0. So at 2 seconds, I'm over here. T equals 2. Okay, S of 3 is 9 minus 12 plus 4. Negative 4. That equals 1, right? 13 minus 12. So then, I'm back here at t equals 3. So I'm going like this. It's kind of like another parabola, yeah. Except you do not have two axes, right? So that's what makes it weird. I never learned one-dimensional graphs, so I remember when I first learned these, I was like, okay, this is weird. Now, S of 4, that is 16 minus 16 plus 4. So that equals 4. So then I'm over to here again. T equals 4. And you could put in 5 and stuff, and you'll see you're going in that direction. Now, just to give us some perspective, right? Let's do a 2D. So this is a one-dimensional. Let's do a two-dimensional. So you can kind of see. So this will be position. And this is time. Okay. And this would be 0. Where did I go? 1, 2, 3, 4. And then time 1, 2, 3, 4. So at 0 time, I was at 4 meters. After 1 second, I was at 1 meter. At 2 seconds, I was at 0 meters. At 3, I was at 1 meter again. And 4, I was at 4. So then you get this graph here. And then for me, because I've been so used to slope being my derivative, I can see where I have negative velocity, 0 velocity, and positive velocity. So if I have positive position and positive velocity, do you see I'm going away from the origin, and that's always the origin. Okay, so there you go. There's your homework, and this too as well. Okay, I'm asking you all these questions, and that's just kind of you're reading the graph. You're not using any calculus or anything at all. You're just reading the graph.